All right, so it's time for part two of the videos on hypothesis testing with one-way ANOVA. This is our between groups one-way ANOVA. So what we want to do now is go through an example of a between groups design and do at least a quick run through of what the 6 steps to hypothesis testing would look like with a between groups ANOVA. We'll follow that up with another video where the example will go far more into depth. We'll actually show how to calculate each of those individually, go through all 6 steps all the way to the end. And then finally, we'll have a video on what we call post hoc tests, which I'll introduce the idea of at the end of these videos. Okay, so our research question here: what influences foreign students, right, foreign students who've graduated from a university outside of the United States to choose an American graduate program? Specifically, how important are financial aspects to the students in arts and sciences, education, law, and business? So this is a bit of a convoluted research question, but I apologize. It comes from the book, so you should hopefully be able to follow along. The question essentially is, if you were an undergraduate in another country and you finished your bachelor's degree and you were deciding to come to graduate school in the United States, maybe you're a student who's going to be in arts and sciences, maybe education, maybe law, maybe business. How important would financial factors be in making that decision to come to the United States? Okay, hopefully that clears up a little bit. So we did a survey of some graduate students. Let's imagine that you're a graduate student already, you have this research question, and so you go around to several of your friends, or perhaps you're at a graduate function and you say, hey, can I ask you all a quick question? You get 17 people to come up and fill out your survey. You end up with, looks like 5 individuals in arts and sciences, and those are their data, then 4 individuals in education, 4 in law, and 4 in business. And so each of these numbers represents their rating on a 1 to 5 scale of how important they felt financial factors were in making that decision. So our first step in hypothesis testing would be to identify our populations. So our populations, and we'd have at least 4 of them in this case, all foreign graduate students enrolled in arts and sciences programs in the United States, all foreign graduate students enrolled in education programs, business programs, and law programs in the United States. Our comparison distribution, then, we are going to be looking to see how the difference between one group, excuse me, the important factor of one group differs from another group and another group and another group. That's a 4-group design. So we know we can't do that with a t-test. So we're going to be doing the ANOVA design. We're going to be looking then at an F distribution, looking at between groups variance divided by within groups variance. Because we have a singular independent variable, type of graduate program, it's got 4 levels. It's manipulated between subjects because each individual is in a singular program. We have a one-way between subjects or between groups ANOVA. Our assumptions then, you'll remember we only have one new one to the between groups design compared to the t-tests. So we know we ideally want our participants to be selected randomly, primarily because this allows us to generalize our results outward and to know that we have these hopefully representative samples that we are comparing. But even if it's not perfectly representative, as long as we're cautious in generalizing, we can still run the test, right? These are robust hypothesis tests. And so in this case, while our participants are probably not randomly selected, we'll just be careful in generalizing our results. It's not clear if our population distributions are normal, but if you look at our data, which we can go back to real quickly here, you can see that the numbers themselves don't appear to be particularly skewed. In none of these distributions is there what appears to be an outlier, right? And so to that end, we can at least on the surface assume that we have met this particular assumption. The new assumption that we have for the between groups ANOVA is the homoscedasticity assumption. Right? We're going to return to this later when we actually do our calculations so I can show you, and I'll also show you then at that point why I think you should do your homoscedasticity test potentially while you're calculating everything else as opposed to on the front end while you're still thinking about assumptions. But as long as you do it and you don't forget, then you're all right, however you want to do it. Our hypotheses. The null hypothesis, the one we're always trying to rule out in a hypothesis test, says that foreign graduate students in arts and sciences, education, law, and business all rate financial factors the same on average. Right? And so we'd be saying that the mean importance that students in the population of arts and sciences, right, that whole population, feel about important factors is essentially equivalent to the mean of the students in education, the law, and the business. Right? They all feel the same about financial factors. The hypothesis that we want to find evidence for, right, ruling everything else out, is our research hypothesis. I'm not saying that there is a difference. They do not all rate financial factors the same on average. Now, it's important to note here that I'm denoting this as a non-directional hypothesis, in part because the ANOVA design cannot test for directionality. I'll show you that later, but essentially the ANOVA finds that there is a difference, not where the difference lies. So we don't actually know which groups differ from one another when we find a significant ANOVA, just that there is a difference at least somewhere. So the research hypothesis can be phrased somewhat non-directionally, knowing that our test is going to be essentially non-directional. That's not to say you can't have very, very specific predictions set up within your hypothesis. Perhaps you feel as though business students, by the nature of their graduate interests, would be particularly keen on financial factors and place maybe potentially higher importance on those financial factors. In that case, you'd have what we call planned comparison, and we'll get back to that at the end of this particular series of videos and talk about how planned comparisons fit into your hypothesis, and then your testing that you'll actually run. So the next step then would be to determine the characteristics of the comparison distribution, right? And so basically figuring out, for this particular example, figuring out degrees of freedom, right? We, in the t-test world, we would also figure out what that mean was of the population distribution, but we do things a little bit differently here in the ANOVA world. So for right now, we're just going to worry about calculating our degrees of freedom. These are slightly new ways of calculating degrees of freedom. We still use the n-1, but we now have different types of degrees of freedom. Before we had between, we had within. Now we have between, within. We can have individual sample degrees of freedom, which we sometimes denote as lowercase n. So let's start there. If we have 5 individuals in arts and sciences that gave us data, and then 4 in each of education, law, and business, then our degrees of freedom for each sample would be computed for each by doing n-1. So for arts and sciences, 5 minus 1, and our degrees of freedom would be 4. And for each of the next 3, because they have 4 in each, it'd be 4 minus 1 would give you 3 degrees of freedom for each of those groups. Right? So a 4, a 3, a 3, and a 3. Between groups, degrees of freedom, calculated by the number of total groups that you have. In this case, we have 4 groups. Then minus 1, we have 3 between groups degrees of freedom. The within groups degrees of freedom is calculated either by the total number of individuals in a particular experiment minus the number of groups. Minus minus the number of groups, or by simply adding up all of the individual sample degrees of freedom. So if you took the total number of people in our experiment, we've got 17. You minus the number of groups, you get 13. So that's one way of calculating it. The other way is to calculate it by adding up each of the individual sample degrees of freedom. 4 plus the 3 plus the 3 plus the 3. Both give you the same answer, right? So you end up with 13. Note that the between groups degrees of freedom, this is looking at how one group differs from another group. Right? And so we're talking about that numerator, that difference between groups or between groups variability. The denominator is all about how individual groups are performing. That's a within group variability. And so that degrees of freedom then is going to correspond to our denominator statistics when we start to calculate our ANOVA. We also still need to determine critical values, right? Just like in any of our hypothesis tests, we need to know what value to compare to know how far into the tail of our distribution our score lies in order to determine the probability of it occurring due to chance alone. If we're using a p equals 0.05 value in this table from the back of your book, which differs just slightly, but it's essentially highly equivalent to the table that I've posted online, and you'll see later on in lectures, it suggests to us that the bolded term there, it says, is for, let's see if I can read this. The bold term then is for 0.01 p-values. The middle term there, the regular type, is for 0.05, which is the one that we use, and then the italicized font is for a p-value of 0.1. So you've got 3 different values depending on the type of p-value you wanted to use in your hypothesis test. We're going to use a p equals 0.05 unless we otherwise have stated, right? And so if we go back to our degrees of freedom, then we had 3 between groups degrees of freedom because there were 4 groups minus 1, and then 13 within groups degrees of freedom. So if we look then at where the 3 column lines up with the row for 13, we get a value of 3.41, and a critical value then, our F critical, is 3.41. Okay, so we use the table essentially the same way we use the t-table. Calculating the test statistic. Well, We're not going to do all of this yet because I haven't even shown you the formulas for how to calculate the sums of squares that we need to go into these particular values. But essentially what we're going to be doing is calculating a measure of between groups variability by seeing how each group differs from the larger population of scores that are in this whole experiment. And so we'll be looking at how the mean of a group differs from a center point of all of the data, right? And we'll do that for each of those individual groups, and we'll add those all together, and that'll give us a between groups variability. That ratio then needs to, or excuse me, that numerator needs to be compared to the denominator within groups variability to create our ratio. And so we'll then have to find out how to take a measurement of variability of one group, variability of another group, and variability of another group and add them together, right? How the scores differ from one another within the context of each of their individual groups. After that, we make a decision, right? And if our calculated test statistic exceeds our cutoff, then we reject the null hypothesis. We say we have found a statistically significant difference. We say that foreign graduate students studying in the United States rate financial factors differently depending on the type of graduate program in which they are enrolled. Right? Now, notice that conclusion. It does not say which group rates financial factors more, which group rates them less, which groups might rate them equivalently. All we can say with a significant ANOVA is that there is at least one, maybe more, differences somewhere between our groups. In order to figure out where they are, we need to run what are called post hoc tests. Post hoc tests we'll introduce in the last video in this series. Like I said, we'll figure out how to do that pretty soon. Post hoc tests essentially are equivalent to, or nearly equivalent to t-tests, right? Okay, so what does it look like to set up the data in an ANOVA? As my mom would probably joke that as a half German, my dad is entirely German, and she blames a little bit of my attention to detail on our German background. She would say that the ANOVA design was built for me because the ANOVA design, unlike any of the other hypothesis tests that we've performed so far, comes with a table for organizing all of the information that you have relevant to calculating your hypothesis test. Now, that might not sound all that great to you, but think about it this way. You've got potentially 7, 8, 9. In this case, you've got 3, 6, 8, 9, exactly 9 different numbers you need to keep track of in order to then test for your hypothesis to see whether or not you have a significant difference. Having a table that tells you exactly where to put them all, and then knowing how each of the positions on the table relate to one another makes it extremely easy to calculate. So if you look at the table down here, what we call a source table for ANOVA, on the far left, you see the actual source of variance, what we've been calling between groups variance, right? The difference between each of our groups, the center points between the averages, and then within groups variance, right? The difference that exists within each group and how the scores don't all line up. Individuals don't perform the same. And then we have a total measure of variance. It's essentially, and is mathematically, the sum of between and within groups variance. So you add between to within, it'll equal your total variance. We then have sums of squares. Right, the next column over, we've been doing sums of squares a whole bunch of times, right? It's just a score minus another score and then squared, right? And so we have a between groups sum of squares, we have a within groups sum of squares, and we have a total sum of squares. And just like with the variability over there, when you add between group sum of squares to within group sum of squares, you get total sum of squares. So again, that's fairly easy. It just adds right down the table. Degrees of freedom. We've already talked about how to calculate between groups degrees of freedom and within groups degrees of freedom. But what I didn't show you before was that if we had 4 groups and 3 between groups degrees of freedom, and our within groups had calculated all the way to 13, well, if you add those two together, our degrees of freedom total then is 16. Again, everything just adds down the table. And then when you get to the next column, this MS, that's a new one for us, and one we'll show you how to calculate when we've got a little bit more data in front of us. Sorry, this PowerPoint likes to keep shifting ahead on its own. The mean square, which is what this MS stands for, mean square, is simply calculated by taking the sum of squares divided by the degrees of freedom. So in the case where we have a mean square between there on top, we have to take the sum of squares. Excuse me, my battery's getting low here. Okay, excuse me. So in the case where we're calculating the mean square between, we simply take the sum of squares between. We divide it by the degrees of freedom between. Right? Fairly straightforward. In this case, you divide across the table. mean square within, you do the same thing within that row, sum of squares within, divided by degrees of freedom within. And now finally, in order to get our F ratio, right, the goal we're trying to get to, this F statistic that we can compare then to our critical value, we simply take the mean square between and we divide it by the mean square within, and we get our F ratio. So that was a little fast, but once you run through the source table a couple of times, you'll notice the relationship. You should be able to pick up on it. And then if I were to say erase a couple of values within it, you should, using a sort of form of source table Sudoku, be able to work your way back and figure out what those missing values were by knowing the relationship between those positions. So again, to sort of elaborate there, column 1, simply identifying the source of the variability. Column 5, I don't know why this is all filled out in a funny way. If we start at column 5, then at the far end, that's our F ratio. That's what we want. That's new. How do we get it? Well, we look to the column to the side over there at the mean square. Mean square between divided by mean square within gives us our F ratio. We can see that in that formula. All right, that's good. So how do we again get to the mean square? Well, if we look to those formulas, it says it's a function of the sum of squares of degrees of freedom, such that across the rows, you take the sum of squares between, divided by degrees of freedom between, and you get the mean square between. All right, and so fairly simplistic way of using the table, and it means that as long as we know how to calculate our sums of squares and our degrees of freedom, everything else is a breeze. Let me show you real quickly how you would calculate that, and then we'll go through another example in the next video. For the sums of squares total, this is all of the variability in the entire experiment. It doesn't care what group they're in. It doesn't care at all that there even were groups. And so what you do is you pretend there weren't any. And so if I have this X column, I put all of my data from all of my groups all in that X column. And even though I've denoted to the side what groups they're in, I'm going to ignore that for now, add them all together, divide by that total number of, I believe it was 17 individuals in the entire study. That will give us what we call our grand mean. So you'll notice in the sum of squares total equation, it says the sum of x minus gm, that's grand mean squared. The grand mean is just the mean of all your data when there aren't groups at all, the grand mean. Okay, so the sum of squares total simply finds that grand mean and then takes each of those individual scores and subtracts the grand mean from them. So you subtract off that 3.588 from 4, do it from 5, do it from 4, do it from 3, do it from 4, and keep doing it all the way down, right, and filling out that next column there. After that, you square all of those deviations together, and we see that last column then where we've squared all of those values. Finally, at the end, we have to sum all of those squares together, right, and when we do so, we get a sum of squares total of 8.122. The next one here, and I'm going to work my way up the source table rather than down. Started at sum of squares total. We're now going to do sum of squares within. So in the sum of squares within, we're looking at variability within a group, right? So how the individual scores differ from the other scores within that group, or the mean of that group. So if that's the case, we need to first figure out what the mean is of each of those individual groups. So I need to add up all the scores in arts and sciences, and I need to divide by 5 because there were 5 total scores in there, and I get an average of 4. I need to do the same thing with education, add up those 4 scores, divide by 4, I get a 375. Do it for law, get a 275. Do it for business, get another 375. Now we've got the means of each of our groups written off to the side. Sum of squares within formula is just like the original sums of squares we did. It's a score minus a mean, and then you square that deviation. And so we take the 4 for our first X, our first raw score in arts and sciences, subtract off the mean of arts and sciences, which is a 4, gives us a 0. We square it, it's still a 0. Do it for each of those. 5 minus 4, and then squared. 4 minus 4, and then squared. 3 minus 4, and then squared. And 4 minus 4, and then right? Then when you get to education, you now do the same thing, but you're using the mean of education, right? So 4 minus 3.75, and then squared. 3 minus 3.75, and squared. Keep doing this. When you get to law, use the average for law, and when you get to business, use the average for business. Once you've got all of those scores calculated across your table, and you have now this giant column of squared deviations, you sum up all of those, you get a 4.256 for this example. You now have your sum of squares within. So if you've got a source table drawn out somewhere, you should write in your sum of squares total. Now write in your sum of squares within above that. And now we need the sum of squares between. You could technically, because of the way they're related, use sum of squares total and subtract off sum of squares within. and that should give you sum of squares between. Well, let's see how to calculate it as well. The sum of squares between then is our between groups variance, how individual groups as a whole differ from the entire group of scores. And so we need that grand mean again that represents the entire population of scores. And then we need the individual means of those particular groups, which we calculated in the last step. So this equation says the sum of squares between is the sum of the mean of the group minus the grand mean squared. Now, a key and something that I see people make mistakes on periodically on this particular step is to ensure that when you do this calculation of mean minus the grand mean, you do it enough times to represent the number of scores you had in the original group. And so if you look at this table, the X data are still included, even though the X data are not used, the raw data are not used anywhere in this particular equation. And so the mean minus the grand mean that's being done there in that first row is the mean of the group, the 4.0 for arts and sciences, minus the grand mean that we calculated earlier, 3.588, and you get a 0.412. But notice that that same number gets written on 5 rows, 1 row for each score in that group, right? So you have to do that 5 total times for the 5 scores that are in that group. Square all of those deviations, then write all those down. When you get to education, you're going to use the mean of education, the 375, minus the grand mean of 3.588. But because education had 4 scores, you're going to do that calculation 4 times. You're going to square it 4 times. So you're essentially just writing the number over and over again. Do the same thing for law and business. There were 4 in each of those groups, remembering to do them 4 times each then. You then add up all of those squared deviations, and you'll have a 3.866. We now have all of our sums of squares, and we already have all of our degrees of freedom, right? And so this is a useful table before I fill it in with the values. If you want a sort of cheat sheet or what you could write down to help you remember how to calculate all of the things in a between groups ANOVA, this tells you the formula instead of the symbol that goes in those places. So the sums of squares between is calculated by the mean minus the grand mean squared. Sum of squares within, x minus the mean squared, total, x minus the grand mean squared, so on and so forth, right? So this is a useful table. Source table for our example, flush it all out with actual values. We put the sums of squares that we just calculated in there, put the degrees of freedom that we just calculated in there. Now we can calculate mean square. Remember that the mean square between, we saw just right here in this table, is equal to the sum of squares between divided by the degrees of freedom between. And then the mean square within is the sum of squares within divided by the degrees of freedom within. So if we take that into this value, then 3.866 divided by 3 will give us our mean square between of 1.289. 4.256 divided by 13 gives us our mean square within of 0.327. And our F ratio is a ratio of the mean square between to the mean square within, so 1.289 divided by 0.327. And finally, we end up with an F ratio of 3.94. Real quickly, we didn't do homoscedasticity. And one of the reasons why I wait is because in your calculation of within groups variability, where you're doing x minus the mean of that particular group, once you've come up with the deviation scores, instead of coming up with the overall sum of squares within, as you need for the ANOVA, if you create the sum of squares for each of the individual groups, then you're only one step away from being able to calculate variance. Remember, variance is just the sum of squares divided by n. In this case, because examples, it's n minus 1, right, the degrees of freedom. So anyway, you'll see that in the next example as well, how that it's a useful place to do that particular step, but you can do it at any point in your calculation as long as you come back to it and do it. So anyway, if we look at the squared deviations for each of our groups as we had calculated them, we've got those listed up here. If we then take that sum of squares, we divide by the n minus 1, and so you see that in the bottom part of this table. The sum of squares for arts and sciences was 2, for education it was 0.75, for law it was 0.75, for business it was 0.75. Divide that by the degrees of freedom of each of those groups to the n minus 1, and then you get a variance that's on that bottom row. If we wanted to do standard deviation, it would just be the square root of each of those bottom values. We need variance. We have unequal sample sizes. That means that our largest variance cannot be larger than 2 times the smallest variance. If we look to education, law, and business, they all have the exact same variance. It's a weird coincidence. They're all 0.251, so it doesn't matter which one of those we pick. Excuse me. The largest variance then is a 0.5. If we compare then 2 times the smallest, we get a 0.502. Our largest variance of 0.5 is not larger than 2 times the smallest because that was 0.502 and that is larger than 0.500, just barely by 0.002. But we have met this assumption. It says that the variability of our groups is approximately equal and thus they are homoscedastic, not heteroscedastic. Last step then is to make a decision. We compare our 3.94 critical F ratio, obtained F ratio to our critical ratio of 3.41. This is greater than, it is further into the tail, it is less likely to be due to chance, therefore we reject the null hypothesis. There is, maybe are, a difference or differences somewhere between our groups. Where? Well, as I said, we don't know yet. This is where we need to run what's called a post hoc test, which is essentially a statistical procedure used to determine if there are differences in pairwise comparisons after you find a significant difference in your ANOVA. So if you find that there are differences somewhere, you now have to figure out where they are. And so depending on how many groups you have several pairwise comparisons to make: arts and sciences to law, arts and sciences to education, arts and sciences to business, law to education, law to business, education to business, all of these various combinations of paired comparisons, right? And you run a comparison test for each one of them to determine which groups are different from one another. The word post hoc means after the fact. It's after the significant ANOVA. There's lots of post hoc tests. There's the LSD test, the Chaffee, the Dunnett, the Duncan. I'm going to show you 2 of them: the Tukey's honestly significant difference, or Tukey's HSD, and the Bonferroni. After that, you'll pretty much understand everything you need to know about the one-way between groups ANOVA. Lastly, how to report this information in APA style. Remember, this is a psych statistics class, and so we need to make sure that we know how to report things according to the American Psych Association. And so after your concluding sentence about differences in financial factors being obtained here, you would then need to put a comma and report your statistics. The results of an ANOVA test start out with an uppercase italicized F. You then open parentheses, none of the rest of this is italic here. You put your degrees of freedom between, comma, degrees of freedom within, close your parentheses, equal to whatever your F ratio was that you obtained, not your critical value, 2 decimal places there. Another comma, a lowercase italicized P, and then again, no more italics, just the letters there. And then depending on whether or not you found a significant difference and you reject the null, if that's the case, it's less than 0.05. If you did not, and you did not find a significant difference and you're failing to reject the null, you can put greater than 0.05 or whatever your p-value was, or you can write the italicized lowercase letters NS for not significant. If you're using software to calculate your statistics, then the software will not give you a critical value to compare to. It will instead give you an exact p-value associated with your F ratio. And if you're using a p-value of 0.05 and you get a p-value of 0.02, then you know you've found less than 0.05, and you can either write that as less than 0.05, or you can write the specific p-value that your software outputs. So you could write equals 0.02.